We will be using SpeakUp for the polls in class. So please either go to the website that is given here in a web browser or download the SpeakUp app on a smartphone. We continue from last week, where we have seen a first overview of the entire TCP-IP architecture, where we have seen that there is the concept of a local area network that is interconnected by using MAC addresses. And if we want to interconnect two local area networks, sorry, before that, I should close the first poll. So as a test for the SpeakUp app, I would like to ask you to fill in this, the answers to this poll. So I see that there are a large number of answers. So I will close the poll, and you should be able to see the results on your SpeakUp app, where we see that there's a huge majority from computer science with a few outliers from other sections. Now, the terms I would like to introduce here are the terms of routers and bridges or switch. The term router means a system that can interconnect multiple local area networks using the IP protocol. And the switch or a bridge, for me, these are synonyms, even though the word switch sometimes is used with a different context. A switch or a bridge is a similar device that interconnects wires, typically, using only MAC layer, which means it looks only at MAC addresses. So the main difference is the addresses that they look. From a terminology viewpoint, a switch sometimes alludes to the fact that this is implemented in hardware, which is the state today, whereas a bridge was typically implemented in software, but that's a difference we will not care about. Let's look at what happens when we look at a transfer from here, from the web server, to a device. Here, a mobile device, that's on the LAN of the left. The left LAN is wireless. So the role of the switch is taken here by the base station. Let's look at what happens when we put all the layers together. So the web server sends a file. Typically, we will first require authentication to be made, so we skip that phase. Once the authentication is made, the web server will send a file as a response to a request from Elaine's device. And this is done by having the web server application code, so the web server Apache, for example, using a socket call. And the socket call looks like, for example, send into a socket. The socket is the name that is given by the operating system to the application to send a data block here. So that's an interface between two layers. Then what TCP will do is this data block will be broken into here 5 pieces, perhaps because it's a big thing, it's a video file or a big image that doesn't fit in a single IP packet. So it's broken into several pieces. Each of those pieces contains a fraction of the object that is being sent here. Then it's passed to the network layer, and what the network layer will do is add to those pieces important things like the IP destination addresses here. So here, this transport layer, in fact, must know what is the destination address, which is Elaine's PC here. How it got this? Well, when Elaine contacted first this server, then there was the source IP address. So this server is responding, is doing a send because it did before a receive. And in the receive, it remembered what is the receive address. So for example, so the address is here stored in the socket and is added to the packet that is sent by the network layer. Then the network layer passes it to the MAC layer. Typically, the network layer is implemented in the operating system, in software, and the MAC layer is implemented mostly in the Ethernet adapter, in hardware, therefore. And the packet that will leave the Ethernet adapter contains the same packet here, which contains the same TCP blocks that are here, plus additional header, which is the MAC address, essentially. The MAC address of the next thing, which is here, the bridge. So this packet now is carried by the local area network, which was shown previously, over physical layer. So the physical layer would translate that into bits, that's an optical radio wavelength. radio wave, sorry, and then it's received by the bridge here. So the packet is the same here when received by the bridge as sent by the Ethernet adapter here. Now, what does a bridge do? Well, a bridge will forward it to another device here, which is here the router. So the bridge will send, in this case, exactly the same packet, but over different physical wires, then it will reach the router. Now, what does the router do? The router receives the packet. Why does it receive it? Because the destination MAC address is the router. So in this red header, there is destination address of the router. So it gets it. Seen from the MAC layer viewpoint, it is the destination. But of course, it's not the true destination. So what the router will do is it will remove the MAC header, will analyze the IP packet and see that the destination IP address is not itself. So it's not itself. It will look at its routing table to know where to send it to, and we'll know that's Elaine's PC. Using the network mask, it will find out that Elaine's PC is on one of its interfaces here, the wireless LAN interface. Therefore, it knows it should send it over the wireless LAN interface, so it will take the same, quasi the same packet. We will see later that there's a small difference. Time to leave will be changed. And we'll send it now with a different MAC header, which is the wireless LAN header, and the destination MAC address, which is the MAC address of Elaine's device. Then this will reach Elaine's device. The different layers will strip all the headers, and then the transport layer will receive all the 5 blocks. This is an optimistic scenario, assuming nothing is lost. And then this will be made available to the application. It might not be immediately delivered. Most applications will need to read it first. So whenever the application does a read here, perhaps it was doing a read before and the read was blocking, so it was waiting on the blocking call, or it will do it later, then it will receive the data block. Voila, this is how all the pieces fit together. Of course, we'll come back to that, but it's important to remember those first elements here. That gives you how networking works today. In terms of terminology, the different packets of the different layers have different names. We can call them all packets, but typically in technical literature, they will receive different names. Packet typically means IP layer. So those are the IP packets. Where the packets that are created by TCP are called segments, and the packets that are visible at the MAC layer are usually called frames. Let me skip this. You will be able to do that in the lab. And let me ask you a little question. Now, let's come back to this example here. We observe a packet from the web server, so here, to Elaine, and we observe it at the point 1, doing things we will do in the lab using Wireshark. We can break the wire, put a system in the middle, and observe all the packets. And then we will observe the MAC address and the IP address. Say what is true. Now we'll start the speak up poll. So if you're attending on Zoom, do we have attenders on Zoom? Quite a few. So on Zoom, you can use Speak Up as well. That should work remotely equally well. The idea of a Zoom poll is that it's completely anonymous. So don't hesitate to say what you really think. I don't know what you really said. I will see only the statistics of the class. So the belief is that by making errors, you learn. I mean, if you raise your hand, then you tend to perhaps not say exactly what you mean. Just here, don't be afraid. I close the poll in a few seconds. Now you should see the result, and the vast majority says A, which is the correct answer. The destination MAC address here is the MAC address of the router, because on the right we have a LAN, and this packet should follow the logic of the LAN to reach the router. How do you forward a packet inside the LAN? By the MAC destination address. So the MAC destination address must be that of the router. The IP destination address, in contrast, is global. IP is internetworking. So the IP destination address is the destination address of Elaine here, and it's not modified by the web server here. So if you've understood that, you've understood it's important that you have that clear, otherwise everything will be confused. So that's one of the principles of how the internet works. We'll see later today that there are cases where those principles are modified with what is called NATs. But in order to understand NATs, we must first understand the normal case, which is here. A few words about the physical layer. The physical layer is not the topic of this course. There is a course and several courses on the communication engineering and also on wireless communication. So it uses specific techniques, but we are exposed to some of it through its performance. So the physical layer transforms bits or blocks of bits, sometimes not single bits, but blocks of perhaps 4 bits, into electromagnetic waves. With a few exceptions, you have also acoustic channels under the water, which is not so good for the whales and other animals that live in the water. So most of the systems use electromagnetic waves, which are either optical cables or most Ethernet are optical, but many also are on coppers. And of course, wireless signal is also electromagnetic. The bit rate of a channel is what matters for us. It's the number of bits transmitted per time unit. It's measured in bits per second. Little b means bit, not byte. A byte is 8 bits. So capital B would mean byte. So typically in communication system, we use bits. And the K and M are the true decimal K and M. So K is not 2 to the power 10, but is really 1000 here. This is called by communication theory people the bit rate of a channel. By computer science people who misunderstood or did not take the course or failed at the course of communication theory, call it bandwidth. Right? So invariably in computer science literature, this is called the bandwidth. And if you talk to Emre Telatar, for example, he will shout at you. He will not shout because he's very polite, but he will frown perhaps and say, well, it's not the bandwidth, it's the achievable bit rate. What's the relation between the two? Well, information theory gives the relation. For example, on a simple model, if you have a channel where the only impairment is Gaussian noise, then there is a relation between the bandwidth and the achievable capacity. That's what information theory tells you. And the bit rate is what a given technology will be able to achieve. It must be less than the achievable capacity. And for many practical systems today, we are very close to capacity. Of course, the larger the bandwidth, the larger the capacity, and therefore the larger the possible bit rate that we will do. But that's not at all the same thing. For example, on the EDSL lines, we have typically bandwidth of 1 megahertz and bit rate, which are not 1 megabit, but 15 megabits per second. Bit rate is different than something that matters also for us, which is propagation. This is shown on this diagram. We've seen already one diagram last week when I spoke of the Y packet switching. Here, that's exactly the same story, but to exercise your intellectual agility, I flipped it. So time is horizontal and space is vertical. Here, this is what happens on the line when you send bits. This is a very simplified diagram. For example, if you use Ethernet at 10 megabits per second, this is literally what happens. If you measure the voltage of the line, you will see oscillations between -5 and +5 volts. And this is literally how some very primitive systems send information. Now, today's systems send much more sophisticated physical layer coding schemes, but it doesn't matter. That for us, it gives the important thing. The bit rate gives the transmission speed, and it gives the time it takes to transmit the number of bits. This is how much time it takes on the horizontal axis. The faster it is, so if we have a Ethernet at very fast technology, like today 400 gigabit per second, then this will be compressed here by technology. How is it compressed? Well, by having systems that are not just binary. Here I send a plus or a minus voltage signal. I can send much more sophisticated things like tones in multi-frequency, etc. And I can, if I have very fast hardware and a very large frequency, gigahertz or multi-gigahertz, for example, I can also go faster here. So the technology tends to make it always faster. Today, on Ethernet, we have 100 megabit per second. That's the cheapest Ethernet if your cables are fairly long and low quality. On very fast Ethernet used in data centers and backbone of operators, you can go to 400 gigabit per second or even a terabit per second. Then when A sends a number of bits to B, then the bits propagate at the speed of light. Of course, the speed of light is very fast, but to do 1 kilometer, it still takes 5 microseconds, which at this, when you're sending data at very high bit rate, is not negligible. And if you go around the globe, that means if you ping New Zealand, which is actually further than just going around the globe, because the cables don't go according to the shortest path, shortest direction, physical direction, it will take 200 milliseconds. Right? So if you do a ping to New Zealand, it cannot be faster than 200 milliseconds, because that's the time it takes for one single bit of information to travel to New Zealand and come back. Right? So this is not negligible, right? So when you call, when you use Zoom or things, and you go really to the other end of the world, that makes a difference here. This is illustrated on this diagram by the delay that happens here. So this delay will not get better over time, because that's the speed of light. That's a physical quantity. Unless there's a major catastrophe in the world, this will not change. Here is some examples of how those things compare. If I have a data center with very short distances, bit rates that are very large, then the propagation time to send a packet of 1 kilobyte, so 8,000 bits, that's a fairly standard packet size on the internet. On the internet, most packets are 1.2 kilobytes, or roughly speaking, that number. I took this round number here. You see that it takes a fraction of a microsecond to propagate and much, much less to transmit the packet. So we see that data centers are in fact limited by the propagation time. Even though they are compact in space, the propagation time is not negligible. On the other end, if you use a relatively low speed ADSL line to go to, for example, the Swisscom next switching center, which might be 2 kilometers away from your home, you see that the transmission time is what limits you. If you use very, very adversarial conditions, for example, you're in the desert and you're communicating over old-style ADSL modem to a base station that is 20 kilometers away from you, then again, you will be dominated by the transmission time because your bit rate is very small. And on the internet, well, it depends on the numbers here. But for example, if I go very far away, if I download content from a server that's in California or in Australia or in South Africa, if the server is really there, we'll see that in reality, most of the time, when we go to a site that appears to be New Zealand, it is in a proxy somewhere in Europe. And that's because of this, because the propagation time tends to be too large to get there. Why do we care? Well, because the propagation time has an impact on the performance of a transfer. The performance of a transfer can be computed by latency, but also by throughput. So throughput is the same as bit rate, but it's the useful bit rate. If I send a packet, then perhaps not everything I'm sending is useful, because this is illustrating here, I may not be able to send it continuously. Here is an example, which is called the stop and go protocol. This is our first example of a protocol. Assume A sends a packet to B. And because the channel is not reliable, we will require to have an acknowledgement, and we continue sending only once we receive an acknowledgement. So I send packet 1. If I receive acknowledgement 1, then everything is fine. I continue, I send packet 2. If packet 2 is lost, or if acknowledgement 2 is lost, then this simple protocol will simply wait for a timeout. And after some timeout, by not receiving packet 2, it will decide that packet 2 is lost and will send it again. This is our first example of a protocol that is a bit like what TCP does. If I am sending data, the channel is not reliable. Here is a solution to this problem. In fact, this is what TCP does when its window is equal to 1 packet. We will come back to that when we discuss about TCP. So this is called the stop and go protocol. It's called this way because we go and then we stop when we have an acknowledgement that's missing. And of course, the timeout needs to be computed to be large enough to cover the round trip time, but not much larger here. Now, what is the performance of this in terms of throughput? I asked the question, if I use this protocol to send packets from A to B, that's a very simple protocol. That's the one that is used, for example, inside a machine when you transfer from one block of memory to the disk, for example, you typically will use this protocol. Here, we will see why. Here. Well, we can compute easily the performance by analyzing cycles. If there is no loss, in the optimistic case when there is no loss, what happens to this protocol? Here I'm showing again the time-space diagram. I'm sending data. This is given by the transmission time. Then there is a propagation time. Then I receive an acknowledgement and I wait until I receive it. So if everything works fine and if there is no packet loss, the protocol will have cycles where inside a cycle I do something useful, I send data, then I wait, which is a waste of time. I'm not using the physical wires at all. Then I receive some acknowledgement, which is also a waste in some sense. I'm not using that to send real data. So all of this is the overhead. So we can compute what is the throughput by seeing that what is the time that it takes to do a cycle and how many useful bits do I send here. And we obtain this formula here that relates the packet length. I'm assuming I'm sending a packet length. That also relates the overhead, which is the length of the acknowledgement. So this L prime here is wasted in some sense. It's not useful. It's not directly useful for the transfer that I'm doing here. And we see another element that plays a role, which is the product of the round trip time, 2D, which is the time it takes for a wave to propagate to the other end and come back. So it's the two-way propagation time multiplied by the bit rate, the rate at which we can send data over this line. In this hypothetical example, the line is used for only one process, for just this stream of packets here. So we see that this is exactly the formula. So we see that the throughput is affected by the inefficiency. If the green acknowledgement is very large, it will not be very inefficient. That will not be very efficient. And importantly, by this quantity here, which is called the bandwidth delay product. The bandwidth delay product is how many bits I can send here during this round trip time, which means those are all the bits that are in the pipes, that are in the cables, that are transmitting over the cable, and that cannot be stopped in particular. And if we apply this formula to the 4 cases I gave before, you see that the throughput of this as a percentage of the line rate is given by the last line here. You see that it varies from very small to very large, depending on which case we are. If we're in a case where the propagation time dominates, then the throughput of that is very inefficient because I send a packet and relative to the time it takes to send a packet, I wait a very long time to get the acknowledgement here. So this is one of the issues that will need to be solved by the internet because the TCP-IP protocols work and should work equally well in all of those 4 scenarios here. This will be the topic of TCP. TCP, of course, does stop and go when the window size is equal to 1. We'll discuss what the window size is a bit later. Of course, TCP will use other tricks, in particular a large window size, to make sure that this works better than that. Voila, that's the end of this very first pass on the global TCP-IP architecture. In a minute, we will dive now into the first detailed study of the IP layer. Are there questions on this part? Yes? So explain again the difference between propagation and transmission. This is explained on this diagram here. Assume there is a cable between A and B, an Ethernet cable. And assume with an oscilloscope, I observe what happens at A and what happens at B. I will see at A the waves that is being transmitted. And how fast I do this movement, here I'm transmitting 1, 2, 3, 4, 5, 6 bits. Right? How fast I do it, that means how large those waves forms are, gives the transmission time. That's the bits per second. If I am at 20 bits per second or 1 terabit per second, I will have radically different times here. Now, when I transmit this and I observe over the wires what happened, I can, for example, split the cable and do a little derivation and observe with an oscilloscope what happens at different parts of the cable. I will observe quasi the same. It will be a bit transformed because there's noise on the line and there might be some distortion. If I ignore this, I will observe the same signal, but the signal does not move instantly. Right? If I put light at one end of a cable, it doesn't come instantly at the other end. For us, it does because the time is in microseconds, and we as human beings, we are not sensitive to microsecond differences. We are sensitive to perhaps a few tens of milliseconds, but microseconds are below our radar screen, so we don't see it. We have the impression it's instantaneous, but it is not. The time it takes here, that's the propagation time. Okay. Now, if this is, assume this is a very long cable that goes across the Pacific Ocean, right, from California to Australia, for example. This time here could be as long as 100 milliseconds. And this time here, if this cable is like today's cable, is at hundreds of gigabits per second, will be in microseconds here for one packet here. Which means when you send packets over a very, very long cable, the packets travel through the cable and they are in the cable from some time. You could do a movie, and if we do an ultra fast resolution video of this, we would see that the packet is traveling in the cable and takes some time to get there, which doesn't correspond at all to our perception. I click on something, I have an impression it's immediate, but it is not. And the bad news is that propagation is incompressible. That's something that we will not improve with new technologies, with new optical fibers, better cables put by Amazon or Google. They will all have the same propagation time. This motivates why there are so-called content distribution networks that will move the content to Europe, for example, even though the source of content is in America, in order to avoid this propagation time. There are other reasons that we will see also when we study congestion control. Yes?
I'm reading that copper has, like, the still light of copper is higher than the one in the optical fiber. So why do we tend to use more and more?
Well, because that is not the primary criterion. In optical fiber, the propagation is much better. So the distortion of the signal is much less in optical fiber than it is in copper. Yes, well, if you go to information theory, you will analyze the quality of the channel. You will see that an optical fiber channel has much less noise, therefore you're able to have higher capacity through it. Which would not mean typically the bit error rate, because typically you engineer a communication channel for an extremely low bit error rate on cables. But what it will mean is that the bit rate will be larger. So of course, that's a function of the distance. You can understand that if you have a cable that's 1 meter long, no matter how bad the cable is, the signal you receive after 1 meter is very close to the signal you had sent. So you don't need very expensive cable. You can use twisted pair telephone cables for that. If you want to send a signal over hundreds of kilometers, only optical fibers are able to do that today. So copper is cheaper, it's simpler to use, but it's limited in performance. But that's topics for the communications. Good. Then we move on to the next chapter. the network layer. So as this picture is showing, the goal of the network layer is to be global. It interconnects everything in the world. With the electrical grid, it's perhaps one of the two major man-made artificial systems, the largest. I mean, the scale of the interconnection provided by the internet is huge. We have billions of devices that are physically interconnected. And that's the goal of the network layer. That's what the network layer does, of course, with being while avoiding to pull cables between all possible places. The IP network layer was initially based on two principles. We will see that there are a few violations. So, but in order to understand what a violation is, we need to understand the principles. So the design ideas were the following. First, remember that the goal was to interconnect all systems in the world, and systems were typically connected locally via local area network. That's the mental setting that was done. Then for achieving its goal, the design used the following features. It uses addresses, which are numbers. We've seen them, 128, 178, 156.15, for example. So 32-bit numbers with IPv4, 128-bit numbers with IPv6. And every interface, so every communication interface, if I have a laptop that has Ethernet and Wi-Fi, then it has two addresses. If I am a router that interconnects many things together, each of its interface, perhaps 10, perhaps 20, perhaps 1,000, each of them will have a different IP address here. So the IP address is the address of an interface here. And the IP address is not an arbitrary number like the MAC address, which is a serial number of the adapter, but it should somehow reflect where in the organization of this global interconnection, where this device is. We will come back to that in detail. And every packet, every IP packet should contain the IP address of the destination. That's, of course, the major principle. And so all of this is valid for practically all layers. But the very specific thing is that when a system has a packet and it analyzes the destination, for example, you're a host, you receive an IP packet, you wonder, is this packet for me? Then you do an exact match. But if you're a router, you receive a packet and you say, what should I do with this router? Where should it go? I am a router, I have 1,000 physical interfaces. Which of these 1,000 physical interfaces should I put the packet onto? For taking this decision, the principle is called longest prefix match on the destination address. Let's illustrate what longest prefix match means. Here I'm showing a small network with 4 routers and 3 hosts. And I'm assuming they're using IPv6 addresses, but because IPv6 addresses are very long, I have a compact notation where A is, for example, this, B.C means that, etc. So this notation here, A means an IPv6 address, and /48 means we take only the first 48 bits of this, which means exactly those 3 words, because one word here is made of 4 hexadecimal digits. So every word represents 4 bits. Every symbol represents 4 bits. So every word here represents 16 bits times 3. That's exactly 48. So assume A creates a packet that has destination BARTs here, which is B.D.H2, which is this thing here. So a string of 48-bit followed by D, which is 16-bit, followed by H2, which is 64-bit. So all of this together is the destination address. What will happen in the routers to this packet? Of course, we hope the packet goes from A to B. Well, what router A will do is it will use its routing table, and the routing table contains not the whole list of destinations, but only destination prefixes. For example, a prefix is B. I write B dot star. In reality, it would be in the form that is written here. We would say B, the /48. That means the first 48 bits of this string here. The dot star is only for the slide here, and it's not written in the routing table as well. Then here, this routing table is simply saying any destination address that starts with B should go to output interface 2. And anything that starts with A should go to output interface 0. So when the router receives this packet, it analyzes this destination address. It says it starts with B, therefore I send it to destination 2. When it reaches router R2, then we have a similar routing table, but we have two overlapping entries. We have two prefixes, B and B.D. So B.D is this one. B would be just the black digits here. So they are overlapping. In such a case, we say that we do the longest prefix match. So in this case, B.D matches this, which is longer than that. Therefore, it goes to number 2. Longest prefix means the most specific prefix. If we have various rules that are given by those routing table entries, you choose the most specific one. That's the principle on which IP routing is based. And the effect in this specific case is that a packet that has destination address B.C.H2, for example, the H2 is the same, but since the address is the complete thing, not just the final 64 bits, this is a different IP address. Here, the table at R2 will say, this doesn't match this one, it matches only 3, so it will go to destination 3. Question? What is the meaning of interface, output interface? Voilà, so that's the principle of the first principle of the internet. Routers have routing tables. The routing tables have prefixes, and if they are allowed to be overlapping, we will see that's a very powerful mechanism that allows to compress the routing tables. And when a router receives a packet, in order to determine where to send it, it should do longest prefix match. At least as long as IP principle number 2 does not apply. IP principle number 2 says, inside a LAN, don't use routers. Which means that if W has a packet to send to P, so you send to the printer, and if the printer is in the same LAN, it should not go via the router. That's common sense, right? You don't want to send via the router, because the only thing that the router would do would be to send it back over the same Ethernet switch to the printer. So why bother the router with that if you can send it directly? So that's the second principle. Inside a subnet, you send directly. That means without going through a router. And as we have seen last week, in order to be able to apply this principle, you need something called a subnet mask. When W sends a packet to P, W analyzes the IP destination address, and by the destination address knows that P is in the same local area network. Therefore, W will not send it to the router here, but it will send it directly to P. In fact, in this case, if W sends a packet directly to P, what do you think will happen if we observe the packet at point 1, which is here on the wires between W and the Ethernet concentrator? That's the switch or the bridge. All those things are synonyms for us here. What will we see? What is the IP destination address that we will see in the packet here? Speak up. I'll close the poll in a few seconds. And we see that the majority says A, which is the correct answer. But a large number of you said C, which could make sense, but it's important to realize today that it's not the truth. This is not how it works. If we use TCP-IP, we must have an IP packet, even if the destination is in the same local area network. We could think that perhaps we could do without it. It's true, we don't need the IP address because we know it's local. But imagine we would do it, then we would need to configure the software such that depending where this address is, whether the printer is on the same LAN or not, things would be handled differently. That would be very awkward. So this is not the way it's done. So A will create an IP packet with destination address P, but the packet will be sent directly. What does that mean? The packet is sent directly to P. What does it really mean? Well, it means the MAC destination address is that of P. That's what it means. If W would have a packet to send to LN, that it would send to the MAC address of the router. But if it has a packet to send to P, it will use the MAC destination address of P. Therefore, the router will not receive it, and we will satisfy IP principle number 2. Voila, this is how the principles of IP are. As we will see in a few more minutes, there are violations of that, but they are very specific and limited to some context. Yes?
Question to the illustration on the slide before. If we look at the packet between switch and P, would the MAC source address be W or the switch itself? Is that updated properly?
If we look at the MAC destination address, the MAC source address here, what do you guess? Well, we will see in 2 weeks when we talk of the MAC address. It will be the MAC address of W. So the Ethernet concentrator is transparent. If you pull an Ethernet cable directly from W to P, or if you put an Ethernet concentrator, from the viewpoint of the protocol, which means what you can observe on the wires, should be the same. Which makes sense, because if recursively, if you ask the same question at the IP layer, if I send from W to P and I put a router in between, what is the source address that I see here? The source address at the IP layer is not the source address of the router. So as the MAC layer is the same. At every layer, in fact, the intermediate systems don't change the source addresses. They do it only when for the other layers, for the layers below. We spoke of IPv4 addresses. So as we discussed last time, they are 32 bits. They can be written, typically they are written most of the time in this form, dotted decimal, with blocks that are between 0 and 255, because the largest number on 8 bits is 255. Sometimes we will find IPv4 addresses written with hexadecimal digits. For example, when for compatibility reasons we put an IPv4 address in the context of an IPv6 address, then we will write them in hexadecimal digits. So we will need to do that kind of conversion. For example, the 200 in hexa is C8, and in binary, that is the string of bits here. If you're not, I guess most of you are familiar with those conversions. If you're not, then it's best to use a calculator. But as we said last week, it's also good to remember canonical values like all ones. 8 bits equal to 1 corresponds to 255, and 4 bits equal to 1 corresponds to the decimal 15 here. The only difficult thing is really decimal to binary, which seems to be easier, but in reality is more complicated. So for IPv6, we will not do that. Here's an example of the network that we had at EPFL last week already. If I look at this box, which is a router, so this is a router between two, it has only 2 interfaces, at least on this figure. It has a local area network, which corresponds to this prefix, 128.178.100. At EPFL, the prefix lengths are, the subnet masks are 24 bits. So we see that all the addresses on this local area network should have the same prefix. They have the same mask, so they should start with the same block here. And here there is another subnet that has a different subnet ID. It's 128.178.47 here. So the router tables are, for example, here. This simple router has only 3 routing table entries. In reality, there are always a few others for multicast and loopback and etc. But the only interesting ones are those three. The first one is 128.178.129/24, which is in fact this, which is, where is the 29? The 29 is this one here, right? And it says anything, any packet that goes to that destination, which is this green local area network here, should go via the next hop, which is given here, which is this address here, which is the address of a router. So the routing tables here, the way I wrote them in the previous slide, which was a simplification, it was only giving the output. In fact, you'd give not just the interface, but also the IP address of the next hop here. So any packet that this router receives that goes for LRC MAC4 will be sent to this router here. Anything that goes to 128.178/16, which means the rest of EPFL, at least of that part of the network of EPFL, there are other parts in EPFL that are 128.179. Everything else should go to this interface here, which is in fact the backbone of EPFL. So it goes south. South is the name of the interface, and IP address is the IP address of the next hop. And then there is yet another entry, 0/0. So slash means the number of bits of the prefix that we're interested in. And 0 in any IP address, 0 is not a valid IP address. It means absence of address. But here the /0 means we have 0 bits. That means it matches anything. Any address matches that. This is called a default route. So what does this mean? Well, this is how longest prefix match works. This is a very compact way of saying, by default, you send everything to the north. The north is going to the outside of EPFL, connection to switch. Switch is our internet service provider for EPFL that gives connection to the outside. Anything otherwise, if it's something that is an EPFL address, you go south. With one exception, because there is this little network here that you don't access via the backbone, but is directly attached to a single router that is connected to me. So the rules are, if you happen to be the green network lemma here, go to this direction. Otherwise, if it's EPFL, go south. Otherwise, when it's not EPFL, you go to the north here. This is how longest prefix match allows us to have only 3 meaningful entries in order to reach the whole addresses in the world here. Voilà, we stop here and do a break. Question before the break?
What does it mean to have different next hop IP addresses for the same interface?
The question is, why do we have next hop, different next hop? Well, the next hop is the IP address of a router. But it goes through the same interface because there is a local area network here. There is an Ethernet interface here. What is not, this is a multi-port network. That means there is a switch. The switch is not shown because the switch does not see the IP addresses here. There are some special IP addresses. In fact, those are the addresses we see most of the time. I mentioned 0. If you have 0 somewhere, it means no address, which we put in the prefix, for example, or in code, when we write somewhere a field and it should be an IP address and it is not yet populated, then we initialize it with 0. Then there is a block of addresses that start with 127. So the block, the first 24 bits equal to this one, means this host. So that's an invalid address outside on the internet, and it means this machine here. In fact, we use most of the time only one of these addresses, is the 127.0.0.1, which is also called the loopback address. This is very useful when you're developing programs that use TCP-IP. Then you can, for example, have the client and the servers on the same machine, and only by changing the IP destination address, you can decide whether you go to your test program locally or somewhere else. You can also use this, for example, to do inter-process communication using TCP-IP sockets between machines in a way that will allow you easily to port some of the processes to different machines. If you want to distribute the operation, then a simple change of address will be sufficient. Then those are the addresses that we see most of the time, the 10 and the 192, a bit less those. Those are so-called blocks. So there are 3 blocks. Here a block with /8. /8 means 1 decimal block, so it means 10 dot anything. This means 172.16/12, which is more difficult to analyze. And 192.168/16, that means if we put anything in those 2 zeros. Those are so-called private blocks. Private means anybody can use them, which is not exactly what private usually means. Those are addresses that are not valid in the internet. They are valid only if you know what you're doing in your local environment. If you decide at home or in this class to make a network with 24 computers interconnected together, if this network does not communicate with the outside, then you have to give IP addresses. That's the principle number 1 of the IP, but you can give addresses from these blocks. At EPFL, for example, when you're inside the network of EPFL, most of the time you will not get a 128.178 address, but a 10 dot something. That's an address that's given, that is used inside of EPFL, that's used in practically all private networks. In principle, with such addresses, you cannot communicate with the outside. In principle only, but in practice you can, and we will see how in a few more minutes with NAT. At home, typically, this is what your ADSL modem will probably allocate to you. It will give to you one of these addresses. Those are the addresses that are for smaller networks. Here, there's only 16 bits. This is here for larger network. There is another block of such private networks, which is used also for, that is reserved for ISPs, Internet Service Providers. So if you want to do the same as what we said before, but you want to do it within the context of Swisscom, for example, then you can use this block of addresses. If you do it inside your local private network, nothing bad will happen, except there is a possibility that the IP address allocated to you by your ISP is one of those. So for us as private users, this is not a private address. This is an address that may be allocated to me by an ISP. So it's used, it's private, but for ISPs. But they should, if the ISP allocates to you such an address, then it should use a NAT to translate it to a valid address because it's valid only within the domain of an ISP. In particular, Swisscom and Sunrise might use the same block and give the same address to different machines. There is also another address which is sometimes used if you start to boot your PC. It works only with Windows, as far as I know, and it doesn't manage to get an address. It will pick one of those. This is a so-called link local address. Link is a word that in some contexts means the same as LAN, which means the same as subnet, local area network. That's an address that's valid only in the context of a single local area network. We could say, why do we need those? Well, in fact, we don't need this because we have MAC addresses already. But for example, imagine you boot a machine that wants to connect to a printer, and this machine and this printer, they have no clue. They don't use DHCP or anything. They cannot use IP addresses because you need either a DHCP server, which is an automatic configuration server, or a manual configuration that you do on your machine. But if you don't want to do this, then you can use those addresses that will be automatically self-allocated by any machine when it boots. It will pick randomly the 16 remaining bits here, the zeros. It will pick randomly one value, and it will try. It will send a ping packet to say, does anyone have this address? If someone says yes, then it will try another address. It will not always work because someone else might have the same address and is sleeping, but that's how it works. And by having that, it will have an IP address, which is automatically configured, and it will be able to talk to other systems, for example, to a printer. So this is how it works when you have so-called automatic configuration of local devices. In IPv6, we will see that this is systematically used. In IPv4, it's a bit marginal. It's used only when everything else fails, and it will still allow you to communicate, at least locally, in a local area network, which most of the time is not what you want, right? You want to go to the internet. Then there are special addresses for multicast. We'll talk about multicast a bit later. Multicast is a radically different thing than IP standard addresses. Multicast addresses are identifiers of groups. IP addresses are principle number one, identifiers of physical addresses. Multicast are logical addresses that are identifiers of groups. So it follows a radically different logic that we will discuss in the module on multicast. And then there is a special address, which is the broadcast address, all bits equal to 1. It is the broadcast. That means I send it to everyone, but this is link local. So here I use the word that you will see often. Link local means it's another way of saying restricted to a local area. So I send if I send a packet with this IP destination address, it means everybody in the same local area network will receive it. But that means also the router will not do anything with it. A router that sees this packet will discard it, might look at it to see in case it is interested, because a router is both a host and a router. So perhaps as a host, it is interested in receiving it, but it will certainly not forward it to any other interfaces. Of course, broadcasts are a nuisance, but they are very practical. If you don't know where the printer is, for example, you can send a broadcast to everyone and ask, are you my printer? So that's the kind of things that are done in local area networks. That makes auto configuration very easy. But of course, if it would not be link local, that would be a catastrophe for the internet. If we had a true broadcast packet, broadcast address for attackers, denial of services would be very easy. You send one packet and then it goes to everyone. Question?
What was the difference? So the IP address result for private network.
This one?
Yeah, and the private address used for ISP only.
Well, as I said, this means it's private for an ISP, which means every ISP can use it. But if you are a customer of an ISP, for you, it's not a private address.
Okay, and so my IP address, if I am with an ISP,
It could be one of those. It could be one of those.
okay. And then that's when I send packets to the ISP that translates my IP address to the rest of the data.
Exactly. When an ISP will send your packet to outside Swisscom, if your ISP is Swisscom, it will need to translate it. Swisscom doesn't do it, but we will see that some ISPs may need to do it when they don't have, for example, an ISP that has only IPv6 addresses, but wants to give an IPv4 service, will give an IPv4 service with these addresses. Right. And all ISPs in the world can use the same block, and the addresses can be used many, many times. Question? Well, I did it on purpose. I mean, the /10 means this is a prefix, and I'm interested in only the first 10 bits. So if I write 164.0.0/10, it means the same thing. Right. So here, for example, I could have written 192.168/16. It would mean exactly the same thing. Okay. When we analyze, when we watch an IP packet on the wire, for example, using tools like Wireshark that you are invited to do, is the part that was in green in what I showed at the beginning of this lecture. That's the part that contains, in particular, the destination address. That's a major field. So one line here is 32 bits. It also contains the source address. The source address is used so that a server, for example, knows whom to reply to. And then there are a number of other things that are more or less interesting. One important field is so-called protocol. So in the context of an IPv4 packet header, protocol means the name of the protocol that is contained in the IP packet. What should be contained in an IP packet? Well, if we follow what we've seen so far, we've seen only two possibilities, TCP or UDP. So this protocol means it's TCP or UDP. We find here a generic idea. You don't know by looking at a packet whether it's TCP or UDP because it's just a string of bits. Of course, we could have imagined that there's a unique identifier of all protocols. And let's say the first 128 bits of anything you write is taken from a big book somewhere that says, if it starts with this list of bits, it means UDP. This is not the way it's done. That would require too much organization of things. And perhaps Microsoft could do it, but that's not the way it's done. So what is inside here, in order to be interpreted, we depend on this. So it's a general principle. One way to understand and know how to decode a string of bits is to have out-of-band information, which is typically given by the layer below. We'll find the same thing, that a MAC header will contain the information that what is inside is an IPv4 packet, for example. So here, an IP packet contains the information that the thing that's inside is UDP or TCP. There is also another interesting case. ICMP is the debugging protocol for IP. It is the IP, Internet Control Messaging Protocol. This is what we use to carry, for example, error messages. This is what we use when we do trace route. We send packets to routers that expire and that have a problem sending it. They reply back with an error message to the source. And this reply that we receive is coded with the ICMP protocol. We'll see other examples of use of the ICMP protocol. Yes?
So there's a limited number of protocols that is supported by IP1, right?
Correct.
So have we already achieved the maximum number of protocols, or is there some place for new protocols that should be supported by?
So the question here, because there's only 8 bits, there's a finite number of protocols. In reality, there's an extremely small number of interesting protocols. So anything that is new is typically on top of UDP. So what is then done is, and UDP uses the port numbers, so you will be able to, by the port number, to know, well, you go to that DNS, for example, rather than somewhere else. There is also another mechanism, of course, which is obsoleted, but is sometimes used in industrial context. You can have a specific protocol here that itself contains another header. This is what you do to extend it to, this is called LLC, for example, protocols. We will see other fields. There is the version here, which is not very useful because the IPv4 has only one version, so it's supposed to be always the same. Type of service, we'll talk about it. It's a priority field, which is practically never used in the internet, but is used in the intranet. For example, you can give different treatment to voice packets because voice packets require very low delay. So IP telephony, in the context of the Cisco network of EPFL, will recognize that the IP telephony packets are different and will put them in different queues in the routers so that they receive better treatment than the standard packet. Question? So the question is about redundancy. I did not catch what's the relation with redundancy? Above, the protocol above. Yeah. Well, in principle, a router doesn't care about that. A router looks at the source and destination address, and that's it. Now, it will know it's an IP packet, and of course, in practice, you also have what are called filtering routers, and also deep inspection machines that might look at everything. So those things might care and classify the packets. They might decide to kill all the IP packets that go to a UDP port so-and-so, for example. They might decide not to accept those. And for this, of course, they will use the protocol type. But as I said, the protocol type today in practice is only one out of a very small number of protocol types, among which we have those 3. We will see also that the protocol type might be IP itself. For example, we might carry an IP packet inside an IP packet when we use virtual private networks or we want to interconnect IPv6 islands over IPv4. We'll come back to that a bit later. We will also come back to a field called the time to leave, which is the important one. that will be discussed a bit later. Here is an example of a mask that we may find in places like ETH, for example. What do you think that it corresponds to? So the poll should be open on Speak Up. I close the poll in a few seconds. And then almost everyone says D, which is easy to do if you have a calculator or if you have a hardwired decimal to binary. So this is 254 corresponds to this. So this mask means that thing here. That means ones everywhere except in the last position, which means it's the first 23 bits. Next question. Here is a small network. I have several devices. I have masks that are given here by the previous question. Which one is a valid address for host H? I propose two addresses here. Is any of the two valid or both? I close in a few seconds. The majority says C, with a large minority saying A, and the correct answer is C. Voilà. Works with a finger. If we look up all the details, we'll see 248 and 249 are in fact in the same, correspond to the same prefix, because if we ignore just the last bit of this green group, then it's the same. And that's a bit the drawback with this decimal notation. It's not so easy to see from addresses whether they are in the same subnet or not. So that's the kind of things you may be confronted with. This problem will not occur with IPv6 because IPv6 addresses are typically written in hexadecimal format. As we saw last week, IPv6 was motivated by the need to increase the address space, and the design decision was that it's incompatible. So here I'm showing a machine that has both IPv6 and IPv4. We call it dual stack. It has the two networking stacks. Because IPv4 and IPv6 are typically in the operating system, then all machines we have today have both IPv4 and IPv6, except if you have an old machine that has Windows XP, but it won't work because of security certificates, as you may know, as of this afternoon. So if you have a not too old, IPv6 was introduced in 1997, right? So you need a really old machine for this to be excluded, but they exist. And if you have a machine that has IPv4 only, then it cannot communicate with a machine that has IPv6 only. A machine that has both, of course, can communicate with both. And the motivation was to keep things simple, and also because it's software, the belief is that most machines that have problems will need to have both. But more and more, we will see devices, in particular mobile devices, that will have only IPv6 because operators don't receive easily IPv4 addresses. Apart from that, it's the same as IPv4, but as you can see, it's much less nice. There's no way you can remember the addresses so easily. They are written in hexadecimal digit here. The routing table is very similar. We see the same thing as before. There's a default route, which means the rest of the world. So this will come back to this sign. It means nothing. It means no bit. Zeros everywhere. Here, the /48 means the rest of EPFL, and the /64 means, /48 means the rest of EPFL, and the /64 means this specific address here. Something that you might see, depending on which system you're working on, is that in IPv6, we typically use link local addresses in routing tables, which means that they don't tell you on which interface they are. So the interface is typically added to the address with like a %2. That's not something that we would ever see in an IP packet by looking at Wireshark, but something you might see in a routing table. It means the IP address that is link local and is on interface number 2. We did not need that. We would not need that if we use the global IP addresses, but for some reason, the IPv6 addresses, the link local IPv6 addresses tend to be used systematically whenever we can. I'm showing here also the IPv4 routing table, because in reality, this router will have both. Remember, IPv6 and IPv4 are considered two different things. So if you're a router that supports IPv6 and IPv4, you have two routing tables. And when an IP packet comes, you know from the MAC header whether it's IPv6 or IPv4, so you know to which routing table you should go. Question?
Could you do me a favor and explain the percentage theory with the interface number and why we don't use IPv4 but IPv6?
Because if in IPv4, the tradition is to give the full address, not the link local address. So if I see the address 128.178.100, I know it is on my 100 local area network interface. So if I am on this switch here, 100 is this part. It is the south interface. So if I analyze by my subnet mask, if I analyze the destination address by applying the subnet mask, I see it is the same as my address here. It's on the same subnet as my south interface. I know I must go south. But of course, if you use the link local, then that information is lost. IPv6 addresses are using hexadecimal digits. Because they are very long now, they are much more structured. For example, we see that an IPv6 address of EPFL starts with a prefix that is the prefix of switch, which was not true for IPv4. IPv4 addresses of EPFL are 128.178. IPv4 addresses of ETH are 129.132, I believe. So they don't overlap. So the different prefixes that switch serves in the IPv4 domain are not overlapping, which means that when a router in California has a packet to send to ETH versus EPFL, it needs to, in its routing table, to have one entry for EPFL and another one for ETH, even though they are both served by switch. With IPv6, it will not happen. With IPv6, a California router will have only a prefix saying this, all of this goes to switch, because in order to go to EPFL, we must go to switch first. But switch has a certain number of IPv4 address blocks that are not contiguous, so they cannot be aggregated into one single prefix. Yes?
There should be 4 numbers in each column, but for example, the 620 refers to 0, 620, or 0.
Well, we'll come back to the columns in a second. We'll come back to this. Right now, I wanted to say that an IPv6 address, because it's much larger, will typically be structured between a provider prefix. Then inside the rest here will be given to EPFL to have its own subnetting, which is typically the pink part here. And then the green one is the host address. But you could imagine that you even have inside EPFL that you have different, larger hierarchy with different blocks here. There are also private addresses, like there is in IPv4. In IPv4, we've seen the 10 dot something or 192.168 are private addresses. In IPv6, it is anything that starts with FD, which is a private address here. So the space is also huge compared to IPv4, which means in particular that it's practically possible for an entity to duplicate its IP addresses, public and private. So you can give, for example, when you change the numbering plan, you make some addresses private or public, then you can simply change the prefix. And also, in principle, if you use an IP private address, you can declare a prefix. You can try to acquire a prefix that is used for your own purpose. Why do we want that? Well, the problem is when you merge private domains. With IPv4, practically all companies use 10 dot something addresses. Now, what happens when companies merge or split? Splitting is easy, but when they merge, Nestle buys, I don't know, some other companies, and then this other company becomes part of Nestle. Then both were using 10 dot something addresses. Then they need to change the numbering plan, which is no big deal, but still is not completely transparent. With this, we want to avoid this, but the private addresses, you would still need different prefixes for different purposes. So if we merge entities, we could still keep the private addresses. That's the kind of games and funny things that people do with IPv6. Because the address space is so large, now people do lots of fancy things, which is why IPv6 is so complicated, because there's room to do complicated things, so people do those complicated things. Now you asked a question about those columns and how IP addresses are written. IP addresses are written by pieces, or called hexstats, which are pieces of 16 bits, which corresponds to 4 hexadecimal digits, except it's not really 4 because we compress by removing the leading zeros. For example, if I have 0620, I can remove the leading 0 here and write it 620. So between two columns, I always have 4 digits. In reality, if I route only 3, that means the missing ones at the head should be zeros. That's one way to compress. For example, if I have an address like this one with lots of zeros, then I can remove them. And if I put an empty space between, or no space between two columns, it means as many zeros as is required to fill in the address to obtain 128 bits at the end. Of course, that can exist only once in an address. So this double column replaces some numbers of 0, but it can appear only once because if it appears twice, you don't know how to split between the two blocks. So for example, this address here could be written in this simpler form as on the right. So those are the compression rules for IPv6 addresses. Here I could even remove the 0 here and put an empty space between the two columns. That would also work. So you have to be able to read this, not very difficult. For example, when we write prefixes, we will typically use this double column to say as many zeros as you want. And here are some examples of addresses here. The block 2000/3, so 3 means bits, number of bits here, not number of hexadecimal digits. So it means anything that starts, if you encode in binary, 2 is in binary 0 is 2, sorry, in binary as an hexadecimal digit is coded on 4 bits is 0010. And /3, that means it includes anything that starts with the digit 2 or the digit 3. So those are the IPv6 addresses that are the normal IPv6 addresses as of today. The people who allocated the IPv6 addresses, they think now, well, the number of bits that we have is so large, that's the numbering plan we have forever. IPv6 will never change. In 1,000 years, we will use IPv6. That's what they think. And therefore, they're very careful. They say, well, perhaps we will still need to give addresses for something else. So we take only a very small part of this, the parts that start with 2 and 3, and those are the addresses we give today. In fact, when we started in 97, we had the 4. We had the addresses that started by 4. And then those addresses were given according to some rules that in the meantime have changed. So therefore, we have now the 2 and 3. So when we did labs in the 90s, we had other blocks of addresses. We see, for example, that switch has received this block, 32-bit, and has delegated out of this block, a block of 48 prefix to EPFL, another one to ETH. And now, as I said before, when switch exports to the rest of the world its block, then it exports only this here. We don't need to say specifically anything because routers that are in America, for example, don't need to know the block of EPFL because EPFL is always receiving traffic from America via switch here. Swisscom has received this block. Then there is a specific block which is called provider independent address. So you receive, for example, EPFL receives its addresses from switch. Now, some companies might not be happy with that. IBM, for example, might want to say, I want my own IP addresses, and whether I'm served by AT&T or Swisscom here or there, I don't want to depend on those. So you can obtain such addresses here. They're called provider independent addresses. And in the lab, we use Teredo addresses. So any address that starts with this prefix, 2000-001, followed by 4 zeros, that's 32 bits, that means 2 hextets, 2001 followed by 4 zeros, is Teredo. What is Teredo? We'll come back to it a bit later, but you're confronted with it already. That's a mechanism to provide access to IPv6 when you don't have IPv6. If you have only IPv4, like unfortunately we have in the EPFL network, then you can tunnel, you can put the IPv6 into IPv4 packet that will reach somewhere an entity that is happy to provide an interconnection service that will receive your IPv6 packets through an IPv4 tunnel, and then we'll remove the IPv4 part of it, and we'll put it on the IPv6 internet. This is Teredo. It doesn't work very, very well in the sense if you download videos to watch YouTube on Teredo, you should expect that there will be lots of hiccups. But for testing connectivity, like we do in the lab, that's good enough. Then there are other tunnels that we will discuss a bit later, for example, 624, which are other mechanisms used for interworking between IPv6 and IPv4. As with IPv4, zeros everywhere means absence of address. The loopback address now is simply 1. So you put zeros everywhere, except the last bit, which is 1, which in hexadecimal notation means zeros everywhere, 0 zeros, and 1 at the end. It means a loopback interface. Then you have, as I mentioned, FC and FD, which means private addresses here that cannot be used on the public internet. And then the link local address, which are an exception in IPv4 that are used when nothing works, but that are systematically used on IPv6. Link local, again, means that's an address that I accept to see as a source address only from another device that's on the same local area network as me. And it means, in particular, a router will never do anything with those packets. If you want to reach a device and the only thing you know is its link local address, then you hope this device is on the same LAN as you. Otherwise, you will not be able to reach it. It is used for automating a number of things, so discovery, and keep making sure when you discover something, you don't flood the internet. Multicast is also systematically used with IPv4, with IPv6. So all the FF.00, so FF something are multicast addresses, and we will see some examples here. For example, the link local broadcast, which in IPv4 is ones everywhere, 255, 255, 255, is this address here. It's a one specific address. And you have other things like all routers. That means all the routers that are in the same local area network as you. This is useful, for example, if you boot your machine and you want completely automatic configuration, then you can ask a question, who is a router that's willing to serve me? An alternative is, of course, to configure in your IP configuration the IP address of the next hop router. But an alternative is to send a question to all routers. And this is a multicast address. That means that's an example of a logical address. It will be received by whoever thinks they are a router, or some malware that is trying to impersonate a router. So these types of addresses are used in the in order to perform auto configuration. The IPv6 header format is not very different, except for one thing: the addresses now are very big. So instead of 32 bits on one line, we have 4 times as much. So the header is 40 bytes. And what was called protocol field in IPv4 is now called next header, which corresponds more to reality. Remember, I said perhaps a protocol field can mean an IP packet because you're carrying an IP packet inside an IP packet. Then it corresponds to saying the next header is again IP. Also, because in IPv6, we want to be able to use what is called header extension. For example, if we authenticate the header with cryptography, then we can sign the header and put the signature in an additional field, which is a header extension. In IPv4, this is treated by extensions of the IP header. In IPv6, it's considered a new header that is added. And of course, the next header should contain also a next header field. So this is changed. For example, if you have an authentication header, this authentication header will contain a next header that says, for example, TCP. Apart from that, it's very similar to IPv4. Let me skip this one and just ask you the question from this. In full, what is the hexadecimal notation for this one? I close the poll in a few seconds. And of course, the answer is B. The trick here is to count that there are 8 hex stacks, 8 blocks, 1, 2, 3, 4, 5, 6, 7, 8. And you just put as many zeros as you want in the part that corresponds to that. So many addresses will be compressed, but that's something you must be able to do, in particular to understand, for example, routing tables. Now, everything we've covered so far is the principles of IP, but the reality, what we see invariably every day, whether we are at EPFL or at home, is NATs. So what is NAT? Well, a NAT is something that was invented in order to reuse an IP address. Typically because an internet service provider gives you one IP address, but you have n devices at home. This is what happens with IPv4 today. You probably have a printer, computers, and if you look carefully into your ADSM modem, you would be surprised how many IP addresses have been allocated, which violates the IP architecture, right? The IP architecture says one interface, one IP address. Now we want to reuse the same IP address for many devices here. We do that also in the lab with VirtualBox. When you do in VirtualBox, you have a number of guest operating systems, and we will see we'll do little networks. We'll have many, many devices, but your physical machine has only one IP address. So VirtualBox will use the same trick. It will use a NAT to make sure that the different virtual machines can communicate with your real machine here, using, as you see here, typically private addresses, which here are 10 dot something in VirtualBox, 192.168 in the case of a NAT at home, for example. So how does it work? Well, the idea is there's no magic. I mean, if we just use the IP addresses, there is a problem. If I have only one IP address for the NAT here, and there are A and B that are both speaking to a same web server, for example, then somehow the server needs a way to say, oh, I'm talking to A and not to B. Since I have only one IP address here, I must use something else. I must use an extension, but I cannot extend the IP header because this is hardwired and all the routers in the world are not happy with your extension of the IP header. So the trick is to use the port numbers that exist in quasi all packets that are in principle used for the transport layer, not at all for routing packets. So this is a second violation. We find a principle if you violate one thing, in order to go back on your feet, you need to violate another one at least to compensate for. So since we reuse the same address and we're not allowed, then we also violate the layering principle. So we use the port number. So the idea is that the port numbers are many, because there's a large space here. And for example, here, the address that is visible here, this address, 130 something, that's the IP. I think it's the power saving, because the clock of the device says it is 11 o'clock in the night. And I think for power saving, it brings down the beamer at 11 o'clock at night. But now the clock is wrong on this computer here. Right? Clocks are important in the internet also for security. When you verify a certificate, you must verify that it's still valid. So if you have an incorrect clock, you will think it's invalid. So we're back on feed. Is Zoom also receiving this? Yes, it's inside. So this is the address I've received. Then when the server sends a packet to machine A or to machine B, then it must make sure that it's using, for example, if this is a DNS query that's responding to A and B, it must come from two different UDP port numbers. Even if by accident, A and B were using the same port number, which may happen if you boot two machines that have the same operating system that do exactly the same thing, perhaps they will pick the same port number. It's not very frequent, but it may happen. So those two machines, A and B, are going to the server. They obtain their local port number, which is the same here. The NAT will translate it. So the NAT will build a table entry. It will say, oh, I see this packet coming from A. It goes to that destination address. Sorry, it comes from this local private address with this port number, and it's a UDP packet. For TCP, it would do the same. And it goes to, I will masquerade it. So when I will output it to the output, I will change its IP source address to my IP address, which is the address given by Swisscom, and I will change the port number. I must make sure there is no collision. So this change of port numbers, if I have a small number of devices, which is typically what I have at home, will do the trick. So when now the server receives those two messages, it believes they come from the same machine on which there are two processes, right? Which is not physically the case. They come from two different machines, but for this guy, there's no difference. It's implemented in NATs. In the lab, we will implement it in IP table here. In the reverse direction, in packets from external to internal, of course, the NAT will translate the destination address. So when the server replies and a packet comes to destination address this with a port number, then the NAT will go to its table and will see, oh, I do an exact match in my table. This corresponds to this IP address and this port number. So the NAT will translate the network address, but also the port number. We call it NAT, network address translation. The correct number should be NAPT, network address and port translation number here. So this is the trick. And this allows you in particular to have private addresses because the address is translated. Now you can use whatever address is of local significance. And this is why we see lots of local addresses here. Now, how does the NAT know, in particular, when a packet comes back from a server, where it knows by observing the traffic? And it makes the assumption that communication starts from A, not from S, which is true for servers, typically. The server is outside the NAT, and when A sends a packet to S, for the first time, so the NAT spies all traffic that comes. When it sees a packet, a combination of source, IP, and port number that it sees for the first time, it will take a new port number, put it in the table, and remember it. As we have seen, for example, if when it sees for the second time another packet, it will choose another packet number. Of course, that causes a problem. If you want to put the server on your local area network, then this will not work. Because the first, for example, you have your home automation system, your heating system that you want to control from here at EPFL. You want to go to this server, this will not work. So you will need to do some work for that. You will need to go into your ADSL modem and manually configure an entry in this table. For example, if you start a server that responds on port 5000, you will need to manually go into the table and write an entry. That is here. This is called with different names. It's called punching a hole in a NAT, or it's also called port forwarding. So this is why you may need to do port forwarding. You will need to do it if you have a server. Voila, that's all that we'll see for today. Thank you very much and enjoy the lab and the quiz.